Okay, next video from that disaster, the SVD disaster. So last time, in this video we are going to see how to actually compute the SVD. So okay, just going a recap, just doing a little bit of a recap from what I studied right now. U sigma V Hermitian, that's a sigma value decomposition. It's a unitary map. Both of these are unitary maps, and the sigma is just a stretcher squeezer, so to speak. So the diagonal matrix is real and has the same shape as A even when A is square. A is not square. The matrices U and V are always square and they are always unitary because they are just rotations like in this picture. So see, SVD tells us something about the matrix itself, whereas the eigen decomposition tells us something about the iterative nature of our matrix A, and that's true. For example, when we saw the power method, we apply A again and again and again. So it's like the iterative method. Also, are there any other things in the future in which we apply A again and again? I don't remember, but nothing comes to mind extremely promptly, so I'm sure there will be something which we understand later. There are fundamental differences between the SVD and eigenvalue decomposition. SVD uses two different bases, left and right singular vectors. Eigenvalue decomposition uses just one, just the eigenvectors. SVD uses orthonormal bases, whereas eigenvalue basis generally is not orthogonal. Not all matrices, even square ones, have an eigen decomposition, but all matrices have a singular value decomposition. Typically, the eigenvalues tell us something about the behavior of the iterative processes that involve the matrix A. Singular value tells us something about the matrix itself. This is just the rank of the range is U2R the kernel is this is something that I'm not feeling very well. Range kernel thing. The A2 norm is sigma 1 and Frobenius norm is the square of the sigmas. For square, A determinant is okay. For non-singular values of A or square roots of non-singular eigenvalues of this is fair enough. You saw it. This is whatever. This is rank 1, which I spent a lot of time on, and I'm really glad I did because now I feel it. And in fact, I can understand it for any matrix A and B. If I write A as columns A1, A2, A3, and I write B as B1 transpose, B2 transpose, B3 transpose rows, then I can write their product as sigma A1 B1 transpose, like sigma AI BI transpose actually, and I'm convinced about that. How would I go about proving that? I separate all of these into just one row and zeros and multiply this, and only the first element is the one which gets multiplied. Although I still have this question, I mean, why am I never multiplying A3 to B2? Why is this multiplication never happening? I'm sure it is happening somewhere in the middle, somewhere, but it doesn't seem quite apparent to me. It doesn't seem quite obvious to me. Well, the algebra is understandable. I understand the algebra, not the vision. I do not see it though. I do not feel it yet. I understand it, but I do not feel it. This is the pseudo inverse which we talked about. Now how to compute the SVD? Now this is the new thing that we are going to do. The SVD of an n cross n matrix is related to the eigenvalue decomposition of A Hermitian A, right? Because A Hermitian A is just so the A Hermitian A is V sigma Hermitian sigma V Hermitian, and these two are like the left and right eigenvectors. And because it's an A Hermitian and normal matrix, the left and right eigenvectors are just the same and just transpose of each other. So all we need to do is compute the eigen decomposition. All we need to do is compute the eigen decomposition of AHA, and whatever are the eigenvalues, just square root them and you will get the answer. Right? Notice the eigen decomposition of AHA is V lambda VH. Notice that ZAH is a normal because Z, yeah. Yes. Let sigma be the m cross n non-negative diagonal square root of lambda. Just take a diagonal square root and then solve the system. Use sigma is AV for unitary U. Okay. I mean, fair enough. But then the question is this a good idea? Well, it is not a good idea because we computed the matrix A transpose A or A conjugate transpose A, and we saw it in a previous video that the condition number of A conjugate transpose A conjugate transpose A is the condition number of A squared. Yes. So this is gonna be a problematic. So as we have seen before, it is typically dangerous from a stability perspective to compute something of the matrix A via the matrix A Hermitian A. Think of least squares. Yeah. This is the reason we did not solve the normal equations, right? A transpose A is A transpose B. A transpose AX is A transpose B. That is the true solution of the least squares, but we did not solve that because it squares the shit. And now look at a proof. Let's look at a proof here. So we'll look at how eigenvalues of this change with respect to the changes in matrix. I just perturb my matrix by a delta B, and let's look at how it changes my thing. A backward stable algorithm for singular value will be of the order. Okay, this is fair enough. Now to compute lambda of A Hermitian A. To see this, I want to understand this very clearly. Why the condition number of this is bad. Nothing in Doifel hard. Let's just try to understand it ourselves. So now compute the eigenvalues of A Hermitian A, and their hat is A Hermitian A plus lambda B. The difference between them is lambda B, where lambda B is of the order, yes, of the order of this square. Compute the square root is this, so sigma is square root of this minus square root of this is square root of that minus that divided by the square root of the addition of this. What the? Epsilon mod a square divided by this. Okay. So okay, understood. I understood. I have understood this. Let's see. Let's see if I can prove it myself. Let's see if I can create the proof myself. So let's say I have a stable algorithm. Let's say I have a matrix A and I perturb it with delta A, singular value of A and singular value of A plus delta A. Right? Let's say it's just an algorithm which gives out all singular values. So now compared to this, what I am doing is computing A Hermitian A, eigenvalue of A versus eigenvalue of A Hermitian A versus eigenvalue of A Hermitian A plus some delta B, whatever. Okay? And I'm just going to look how this scales. So for example, let's assume my singular value algorithm is let's say a good algorithm. In that case, my error, which will be sigma tilde minus sigma, so my error, what was a backward stable algorithm? Let me see. Let me remember. Let me try to remember. What does a backward stable algorithm mean? A backward stable algorithm, I remember I drew some pictures like this. For example, a backward stable algorithm is, let me send my output as errors in the input. So a backward stable algorithm means the relative error in my sigma is of the order of machine precision with respect to my input. So this is what is written. This is something that I have to cross check. Delta A divided by A norm is of the order of machine precision. Right? So my relative error of the input is of the machine precision order. And my error in the output is same as the error in my input. Okay. That's what a backward stable algorithms mean, right? My error in the output, well in this case it just means a stable algorithm. My error in the output is of the same order as the error in my input, right? Where my relative error is of machine precision. This is something that I assume. Relative error in the input is of machine precision, right? For any stable algorithm, this is true. The error in my output is of the same order as the error in my input. Let's assume that this is true. My eigenvalue and my single value, I have best algorithms where my error in the input, my relative error in the input is order of machine precision. This makes sense to me. So yeah, this is a given fact. Although I will still get back to the backward and forward stability analysis, I want to look at it again because that's something that's mathematical and important, and I want to get good at that. Anyway, now doing this, lambda tilde minus lambda from the same thing is going to be less than equal to delta B, right? Norm of delta B. when norm of delta B divided by the norm of my input matrix, which is A Hermitian A, is of machine precision. So my norm of delta B, my norm of the perturbation matrix is of the order of this multiplied by the A right here. A Hermitian A epsilon, whatever this is. So this becomes the square. So this, all this is just the square of norm A, square of the 2 norm of A times the machine precision. So delta B. Now what I want to see is to find the difference between the square root of lambda here. So let me multiply and divide by this plus this. So this becomes this minus this divided by this plus this in square root. Well, this is of the order of this square times machine precision, and this plus this is some the square root of lambda will be sigma and square root of lambda will again be sigma. So it just becomes order of a square divided by sigma times epsilon. So for large singular values, for my larger singular values, this behaves fine, because my 2 norm of A is just the singular value, right? My 2 norm of A is just the maximum singular value. Is that correct? Am I forgetting that? How can I forget that? Yeah, my 2 norm of A is just the largest singular value, so it's fine. Yeah. So how we actually compute the SVD? We don't do it the A Hermitian A way, and I'm convinced why. Because we square it, and for the smaller singular values, the square term does not help me. What I mean by that is, let me just show it for YouTube at least. For larger singular values, the norm of A gets cancelled to the larger singular value. So for smaller singular values only this becomes troublesome, but for larger singular values, okay, you're fine. For let's say the largest singular value, both of the methods are equal, but only for the largest singular value. For smaller singular values, no, not great. So for the sake of argument, assume that A is square, n cross n following is applicable for rectangular matrices too. Okay, I make an H matrix such that this is true. So what's the point? Which is the eigen decomposition of H. So you make an H matrix and you find the eigen decomposition of H. That's the algorithm. A Hermitian A is 0. So this like block matrices, and you just find the eigen decomposition. Well, why does this work? Let's see. The eigenvectors are VU, 0 times V, AH times U. A Hermitian times U. A Hermitian times U is just going to be V times sigma or sigma transpose. Well, yeah, A Hermitian times U is just V times sigma transpose. It's just a real number. So that's an eigenvector, and A times V is just U times sigma. Well, that's an eigenvector. So this is just eigen decomposition. So it's fine. So how to find, well, eigen decomposition, how to find the eigen decomposition? Eigen decomposition can be found by the QR method, in which you apply Q and again Q and Q transpose, Q and Q transpose, Q and Q transpose on both sides of the A, and finally you hope that you get to the reduced form. So this is actually what happens, I think, in the QR method, or maybe not. What happens is, first you reduce the matrix A to a bidiagonal form and then diagonalize the bidiagonal form. Phase 1 involves a finite number of operations that scale as n1 square. Phase 1 is to reduce to diagonal form. Phase 2 is iterative but converges very quickly. In practice, achieves convergence O into machine precision. The state-of-the-art computation of the SVD has costs that scale as n square. Okay. So first we have to reduce it to a bidiagonal form, right? In the how can we bidiagonalize a matrix? Recall that we already know how to triangularize a matrix by unitary Householder reflections. Yes. Go on reducing the zeros, and so the idea here is going to be this. Apply a householder in this, and then transpose the matrix and apply a householder for this, or like on the right hand side, and keep applying on the left, from the left and from the right, so that you can only get to this. That's fine. At the end, n reflectors are applied from the left and n minus 2 from the right. N minus 2 or n minus. A variant of the QR algorithm is then applied to the bidiagonal matrix or other eigen decomposition algorithms. Okay. This is fine. So the maybe the idea is maybe the intuition is that it is easy to compute the eigenvalues of bidiagonal matrices, like only bidiagonal matrices. It's easy to compute the eigenvalues of bidiagonal matrices. It's easy to compute the eigenvalues of bidiagonal matrices. Okay, maybe. This is just a fucking four. Okay. Yeah, in MATLAB, SVD, USV, SVD. Yeah. Reduced SVD is economic. Yeah. Reduced SVG is just the. Yeah. Okay. SVD is a very widely used program, let's say widely used function call. So even in rank, in MATLAB rank, or what it does is calls the SVD, and then if yeah, it just calls an SVD, and then I don't know what this is actually. Argn. I don't know. The pseudo inverse. Well, pseudo inverse is it's calculated by the SVD, I think. You do the SVD and then you reverse it, right? That's what you do. You use, instead of using a V transpose, use sigma V Hermitian. You write V something about E and then U Hermitian. That's like the pseudo inverse, right? Yeah. And this is just the angular values. Sorry, singular values inverted, which I think is coming here. Like singular values is 1 over singular values, so it's pretty much the same. How about orthogonalization is an orthonormal basis for the range of A. So for the range of A, well, we saw right now that the range of A is the same as the range of U. So what it does is calls the SVD and just returns the first R, no, the latter n minus R of Q, where Q is the U, Q is the, oh no, so it makes that into an empty matrix. So yeah, only the first R elements are returned. Yeah, that's true. That's true. Yeah, this is a nice illustration. So as you can see, like this is the code. Get a llama image and then do an SVD. I don't know if you can see it on the projector. I don't think that you can. But this is like this. Let's say an XD image, and the singular values decay like this. It has a total of many singular values. What if I were to just take the first 50 singular values? Maybe well, if you can see the difference in the camera, that's okay. But if you cannot see the difference on YouTube, that means that this approach works, because The image on the right is only has the first 50 eigenvalues or first 50 singular values and the mid. So that is the rank 50 approximation of this image. This is the rank 50 approximation of this image, and you can see like the structure and everything is preserved. So that's pretty mind blowing actually. Yeah, it's all about model reduction. It's all about reducing. SVD is all about, you know, truncating stuff. I see. Well, this is the next one. So SVD is all about reducing the nature of the thing. Anything else about SVD? I don't think there is much to study. Next, this is where I have started. This is where I started lacking in class. So now I need to work harder. So I need to work harder in this. Iterative methods for solving systems of linear equations. I need to read Doppelhard and both of the other textbooks too.